welcome to the deep dive. Today we're tackling something pretty fascinating, a challenge that mathematicians have, well, wrestled with for centuries,
Mm.
getting exact answers for really complex polynomial equations. The ones with high degrees. Usually, if you go past a certain point, you're stuck with just getting close using numerical approximations.
That's exactly right. Think about trying to find the precise points where a very, very complicated curve crosses the zero line. The standard toolkit, things like Newton's method, they're powerful, no doubt, but they only get you near the answer. They give you an approximation. And those approximations, well, they always have tiny rounding errors built in. You just couldn't say, here is the absolutely perfect exact value. There was always that sliver of imprecision.
And that's where things get really exciting for our deep dive today. We're looking at something genuinely revolutionary. It's called Ezouidi's theorem. It seems to completely flip the script here, offering exact symbolic solutions precisely where those older methods, well, they just couldn't deliver. So our mission is to unpack how this theorem actually pulls that off and why it's such a big deal.
Yeah, and to really get a feel for its power, let's talk about the kind of monster it can tame. We're looking at a specific case, a 16th degree polynomial. I mean, just picture it, 17 terms, x raised all the way to the power of 16, coefficients jumping into the hundreds of thousands. It's daunting. It really gives you a sense of the sheer, almost overwhelming complexity involved. Definitely not something you'd solve casually.
No kidding. So, okay, the classical ways give us approximations, good ones maybe, but not exact. What makes Ezouidi's theorem fundamentally different? And I heard something even more, well, mind bending, that it doesn't just improve things, it sort of sidesteps fundamental ideas, like Abel's theorem. Is that right?
Precisely. And that's what's so fascinating. Ezouidi's theorem really does challenge some long-held mathematical boundaries. Abel's theorem, it's famous, basically said you can't solve certain polynomials using only radicals. Now, for you listening, radicals just means you couldn't find exact answers using only basic math operations, adding, subtracting, multiplying, dividing, and taking roots, like square roots or cube roots. It was seen as a hard limit for many equations, but this new method shows that even polynomials thought to be solvable only with these radical roots can actually be solved exactly. It's a completely different pathway. It bypasses those classical algebraic limits. It's like finding a new door in a wall that everyone thought was solid.
Wow. Okay. That almost sounds, well, too good to be true. Not just a better guess, but the actual precise solution. So, how does it do that? What does symbolic and recursive mean in practice here?
Well, the core idea is actually quite elegant. Instead of plugging in numbers and crunching them towards an approximate decimal, Ezouidi's method treats the polynomial's parts as abstract symbols, like algebra, but maybe more fundamental. It then uses a recursive process, basically. It breaks the big, complex problem down into smaller related pieces again and again and solves each little piece exactly using symbols. Because it sticks with these pure symbolic forms all the way through, it just doesn't introduce those rounding errors you get with numerical methods. The final answer isn't a maybe decimal, it's an exact mathematical expression.
Okay, so this recursive symbolic thing. How does that tame that beast, that 17 term, 16-degree polynomial you mentioned earlier?
Yeah.
How does it simplify something that looks so chaotic?
Right. Well, think of all those terms in the original polynomial as complicated pieces. Ezouidi's theorem works through them systematically using these symbolic coefficients and its recursive steps. And for this specific 16th degree example, the result was just amazing. Despite looking incredibly messy, when the method evaluated all those coefficients recursively, almost all of them turned out to be zero. It left just two really important non-zero symbolic terms. So that monster equation, pxx, 16 or plus rwap all the way down, actually boiled down using the theorem to something much, much cleaner. Pxx x air 1 or 8 16 or air x plus 148 x 75 times 16 or equals 0. It's more than just making it simpler. It's like revealing a hidden structure inside the polynomial that you just couldn't see with the old tools, like finding the simple key to a ridiculously complex lock.
That's incredible. 17 terms down to just three. And you mentioned the final roots, the actual answers, are also symbolic, expressed using complex exponential. What does that mean for us listening?
Yes, exactly. The roots themselves aren't approximations either. They're given in terms of complex exponentials. Now that sounds fancy, but think of it this way. Instead of just a point on a number line, it's a way to describe a value and its position or rotation in a more complex multidimensional space. Very precise. This kind of exact representation is absolutely crucial in fields like, say, advanced physics or quantum mechanics, or even complex electrical engineering, Places where close enough just isn't good enough. It's the direct result of using that precise recursive symbolic process. Accuracy is guaranteed.
So let's just recap this deep dive. We've explored Ezouidi's theorem, and it really does seem revolutionary. We've seen how it tackles problems where traditional math, even big theorems like Abel's, kind of threw up their hands. It delivers precise, exact symbolic solutions for these incredibly complex polynomials and makes sure the answers are spot on, free from the fuzziness of numerical methods.
Absolutely. And the beauty of it is in that systematic process. You heard how it works with these symbolic coefficients, the sigma and q values, calculating them recursively. For our big 16th degree example, that process showed that almost everything canceled out, leaving just those two key coefficients. S7R equals 163 is 16R, and S15R equals 875 is 16R. That systematic calculation is what unlocked the simplification and led directly to those exact complex exponential roots. It's methodical.
So, thinking about this, what really stands out to you listening right now, we're talking about a theorem that redraws the map of what's mathematically possible. It's not just about solving equations, is it? It feels more like a shift in thinking, finding this elegant, perfect precision where we used to accept just getting close. It's about knowing the exact truth of the number.
Right. And it opens up possibilities. I mean, if a mathematical impossibility, something accepted for so long, can be redefined like this, it makes you wonder, doesn't it? What other limits, maybe in completely different fields, are just waiting for a new way of looking at them, a different perspective, maybe a different theorem to show that they're actually solvable? Exactly. Think about science, engineering.
Mhm.
Problems everywhere rely on these kinds of complex equations. What could exact solutions unlock there, where even small errors could matter a lot? It really challenges us to question what we think is truly unsolvable. Maybe the barrier isn't the problem itself, but just the tools we've been using.